Hello, so in this video we will talk about how we can find a regular expression for any finite state automata. So remember that earlier we did the other way around. We said that we can find a finite state automata for any regular expression. Now we are doing the converse of that statement. Okay, so as a recap, let's talk about what is a regular expression. So they are defined, regular expressions are defined recursively over any finite set which is I. So we have a symbol which is null set is a regular expression. The symbol empty string lambda is also a regular expression. And the symbol x is a regular expression whenever x belongs to our input set. And then we have this recursive part here. So if a and b are regular expressions, then the concatenation of a and b, the union of a and b, and the clean closure of a and clean closure of b, of course, is a regular expression. And any finite combinations of concatenation, union, and clean closure is also a regular expression. Okay, now we talk about how we can find a regular expression given a finite state automaton. Okay, so what is our way to do it? We do it by construction. So we say that okay, if we are giving a finite state automaton, we proceed by finding an equivalent finite state automaton which is non-deterministic in the following manner. So we create a new single starting state by introducing transitions from the new starting state to all the old ones at input lambda. So for example, we have, although this hardly happens, that if we have two starting states like this, then we can make it as one. This is a starting state. So we make another new starting state and we say, okay, this is a empty string, this is an empty string. So let's say this is A, this is B. So we make another one with A and B like this. Okay, the next thing says creating a new single accepting state by introducing transition from all the old accepting states to the new accepting states. So for example, just says that if we have this situation, two accepting states, so then what we do is we make both of them non-accepting, and we put a transition like this. So if this is A and B, so this is my A and B, and this is my new ending state or accepting state. You can call it any symbol you want. Okay, and we start eliminating states until we have the following situation. Then we have some following situation is like this. We have a starting state, so there should be an arrow here. We have a starting state and we have some expression here, and we have an accepting state, and what we have to prove is that this guy, so to show that this guy is regular. Okay, so this guy is regular. Okay, now we talk about method of state elimination. So whenever, remember, we want to eliminate states. So what do we do? Whenever we have a situation like this, that we have an input A, then a state, and then an input B, so we can just make a transition. We can just replace this situation by a transition which is A concatenated by B. But this you can easily appreciate that when we have a situation like this, then an input A comes to state S, and then input B comes from state S. So then going from this point to this point, we need an input of A and B. So B should follow A. So this is exactly what A concatenated by B means. If we have a situation of parallel like this, if we have a transitions like this, A and B both go into S, then what do? We do it in two steps. So then A can lead to S and B can lead to S from this point. Okay, so then this means A or B can lead to S, which in other words A plus B can lead us to S. And then we have a C here, and then we do we do the same thing which we did here. We just concatenate A plus B to C, so we get A plus B concatenated by C here. Now if we have A and then there's a transition from S to itself with an input of B, so then this is the situation of clean closure here. So now note that any number of these inputs I can have to stay at S. So and also we have another option when I don't want to stay at S. So this means there is no B input, so I can still go from here to here by A C. I can go A B C. I can go A B B C. and so on. So this means that I can go any combination of B, which also includes no combination of B using a empty string. So this means I have A, B star, C here. Now this is a situation, the same situation, but I have actually extended this to the loop from one state to two states now. Now we have, in order to go from here to here, I can have A, B, D, simple, or I can have A, B, C, B, D. Then I can have A, B, C, B, C, B, D, and I can have any combination of C, B's here. So this means I have A, B, then I have a C, B star, and I have a D in the end. So these are the rules which we will be using to show that we'll be using to eliminate states. Okay. So now if we do that, what happens? What happens is that note that all the eliminations lead to concatenation, union, or Kleene's closure. So we don't see any other operation here except concatenation, union, or Kleene's closure. And since there are finite number of states, why are there finite numbers of states? Because we have a finite state automaton here. The final expression will be made of a finite number of above mentioned operations. So what does it mean? We have finite number of above mentioned operations, which means finite number of concatenation, union, and Kleene's closure. So this is exactly this situation which we studied in the definition of regular expression. So this means that our final expression will be a regular expression. Okay, so to demonstrate this, let's do an example. Okay, so our job is to reduce this into a situation like this. Okay, so what is our first step? All our starting states will have one single starting state. So we can keep this as starting state because we have only one starting state. Or if going by strictly by the definition, we can also have a new starting state with an empty string transition to this state, but that is not necessary, so we don't have to do it. But we have now two accepting states. We have S0 and S2. So this step will tell us that now we want another accepting state. So let me draw it here and I'll call it S3. Okay, and then my S0 is still the starting state, but not anymore the accepting state or final state. And my S2 is not anymore the final state. Okay, rest of the transitions are the same. So rest of the transition I have the same story here. Okay, so if we have a 0 here, we have a 1 here, and we have a 0 here, and we have a 0 here. Okay, what is the next step? The next step is that I want to remove S1 here. So this is the same situation as this situation. So from S0 to S2 the path is 0 and then a transition of 0 here, a self transition at 0 here, a self loop, and then we have a 1 here. So then the next step is I have S0 and then I have S2, and this is the starting state of course. I have S2, and what should I write here? I should write 0, 0 star, and 1. Okay, because of this guy here. Okay, and then I have, of course, I have this guy still there, and I have this guy and this guy, and this is a final state S3. Okay, so this is the situation right now. Now what to do? Sorry, this should be 0, not 1. Now from going from S0 to S2 I have two paths. I can go from 0 or I can go from 0, 0 star 1. So this is the situation here where I have two paths going to S where A and B is there. So this means they are unioned, or the plus operator is used. So what I'll do is I'll do this. So this is S0 here, and then here I should write 0 plus 0, 0 star 1, and then we should say S2, and then we have the same situation, lambda here, and this is the final state here. And of course I forgot this one here. Of course I forgot this one here, so this is S3 here. Okay, now this and this is what situation? This situation is again this situation. So I can say only one path from S0 to S3 with the situation of this 0 plus 0 0 star 1 and then 1 star and then lambda, and then I have again another one with lambda. Okay, so now I can just say, because they are also parallel, so this is S0 here, and then I can say S3 here, I can say lambda plus 0 plus 0 0 star 1 1 star lambda. So now if you want, you can remove this lambda, because anything concatenated with lambda is that thing, but even if you keep it, it's fine. Okay, so this means that this is the expression which is related to this finite state automaton. So in other words, this is the language which is accepted by this finite state automaton. Now, is it a regular expression? Of course it is, because it is made up of finite combination of unions, concatenations, and Kleene's closure. Okay, so in this way we can constructively prove that any finite state automaton is is related to a regular expression. Okay, or the language which is which is derived from a finite state automaton is regular. Okay, so earlier we said that every regular expression, for every regular expression we can find a finite state automaton. In this part we proved that for every finite state automaton we can find a corresponding regular expression. So combining these two, we have the Kleene's theorem, which says an expression is regular if and only if it can be represented by a finite state automaton. So okay, so this is it about this part of Kleene's theorem. In other words, we have proved that for every finite state automaton we have a regular expression. Thanks for watching. Hope you like the video.